In this presentation, we learn about Euclid as well as extended Euclid algorithms. These two algorithms forms basis for RSA algorithm. In RSA algorithm, we know that there are certain variables. What are all the variables in the RSA? Number one, P, Q, which are prime numbers. Then we have product of these prime numbers, which is n. Then in the next step of RSA, we actually calculate Euler's totient value of n, which is psi of n, which is further calculated as p minus 1 into q minus 1. Then we have another variable called e, which is a random integer, and the condition for this random integer is supposed to be a positive integer, and it should be relatively prime to psi of n. What does it mean? It means the GCD of psi of n and e should be 1. Then finally, we have one more variable called d, wherein which d should be multiplicative inverse of e. When we multiply e and d, we are supposed to, it should be congruent to 1 at mod psi of n. So these are all the variables in RSA. Using these variables, we generate the keys in RSA algorithm. Now the question is, if you observe these E and D, we have steps like calculation of GCD and calculating multiplicative inverse. How do we do that? To do that, we have Euclid algorithm and extended Euclid algorithm. These two algorithms help us in finding a number which is a random integer e and its corresponding multiplicative inverse d. Let us see how these algorithms help. We all know that given any two integers, if we have, when we have the divisors of these two integers, we are looking for common integers, and among them we are looking for actually the greatest common number, the greatest common divisor GCD. So how do we get that? The GCD of any two positive integer is nothing but the largest integer which can divide both these integers. There are two facts on which the Euclidean algorithm works. The fact one says GCD of any number and 0 results in the same number, whereas the GCD of two numbers AB results in GCD of second number and remainder of A and B. So means this is an iterative process of finding the GCD, wherein which during each iteration we are going to assign B value to A and the remainder as B. So it's an iterative algorithm. So let us look at the algorithm. So this is the process of Euclidean algorithm, wherein which when we are looking for GCD of two numbers AB, we take two temporary variables R1 and R2. So R1 is equal to A, R2 is equal to B. That fetches us the remainder R and as well as the quotient Q. So how do we get the quotient? We all know that when R1 gets divided by R2, R1 is nothing but R2 into Q plus a remainder R. So R is nothing but R1 minus R2 into Q. So now let us see here how the Euclidean algorithm process iterates. When we get the remainder, the B value gets assigned to R1, the remainder gets assigned to B, and this process continues till we get the remainder value 0. When we get remainder value as 0, the corresponding R1 is the GCD of A comma B. Let us look at how the algorithm is written from the given process. Initially, we take R1 as A, R2 as B, then we iterate till R2 is greater than 0. So as you can see, we calculate the Q coefficient and the remainder R as we discussed earlier. Then we reassign R2 to R1, R2, R2, and this process continues till we get R2 as greater than 0. Finally, when R2 becomes 0, the GCD is R1. When we get two numbers GCD value as 1, then we say that A and B are relatively prime to each other. Let us take one example. Imagine you have two numbers AB. A is 2740, B is 1760. How do we get these GCD of these two numbers? We assign R1, R2, and we calculate the coefficient and corresponding remainder. So you can see that R2 is assigned to R1 and R is assigned to R2. The process gets iterated till we get remainder value as 0. Once remainder is 0, we take the corresponding R1 value as the GCD. So the GCD of these two numbers is 20. This is how we check what is the GCD value, and we are actually looking for GCD value 1. If GCD is 1, then we say that these two numbers are relatively prime. What is extended Euclid algorithm? Extended Euclid algorithm extends the Euclid algorithm by not just finding GCD. In addition, it also finds two more variables. These variables are called S and T. So we find these variables S and T satisfying the equation S into A plus T into B results in GCD of A comma B. Our regular Euclid algorithm finds only the GCD. Extended Euclid algorithm finds two more variables called S and T satisfying the equation S into A plus T into B is equal to GCD of A comma B. Let us look at the process of extended Euclid algorithm. Here we are going to find two more variables S and T. So what we do, we take two more temporary variables for S, which are nothing but S1 and S2, two temporary variables for T, T1, T2. If you observe, the process of Euclid algorithm is same here, where we are finding the GCD, and you can see here the process for finding the S variable, the process for finding the T variable. The process for finding S variable goes this way. We take two temporary variables S1 and S2. S1 is assigned to 1, S2 is assigned as 0. On the T side, T1 is initialized to 0, T2 is assigned to 1. And from this, we calculate S and we calculate T. Subsequently, we reassign S2 to S1, S2, S2. Similarly, T2 to T1, T2, T2. The same process that what we have followed for calculation of the GCD, we calculate the same way S as well as T variables. So the moment we have the R2 value is 0, we get the GCD, which is nothing but the R1 variable. Corresponding S1 is the S variable, corresponding T1 is the T variable. This is the process of extended Euclid algorithm and finding two variables S and T. Let us see with an example. Before that, let us see the algorithm. As we discussed, R1, R2 are the variables used for calculating the GCD. S1, S2 are used for finding S. T1, T2 are used for T. So S1 is assigned to 1, S2 is assigned to 0, T1 is assigned to 0, T2 is assigned to 1. So this is the initialization process. And subsequently, when we enter into the looping structure, we are going to execute this loop till R2 is greater than 0, and we find the quotient by calculating R1 by R2, and this is how we update R to find the GCD, and this is how we update S S is calculated as S1 minus Q into S2, and similarly T is also calculated as T1 minus Q into T2, and we update S by S1 is equal to S2 and S2 is equal to S. The way we have seen the process for GCD calculation, and the same process is for both S and as well as T. Let us look at one example. We have two variables A, B, and the numbers are 161 and 28. We are asked to find extended Euclid algorithm on this and identify what is the GCD as well as the two variables S and T. So you can see here R1 is assigned to A, R2 is assigned to B. We calculate the quotient 5 and the remainder R. Initially S1 is assigned to 1, S2 is assigned to 0. We calculate S by verifying S1 minus Q into S2. Similarly, initially T1 is assigned to 0, T2 is assigned to 1. We calculate T by assigning T is equal to T1 minus Q into T2. Next we update by reassigning R2 to R1, R2, R2. Similarly, S2 is assigned to S1, S2, S2. Similarly, T2 to T1, T2, T2. And the process continues till we get the GCD value by R2 as 0, and we take the GCD as 7, and S1 is minus 1, T1 is 6. This is how we use extended Euclid algorithm to calculate two more variables S and T along with the GCD. Now the question is, how do we use this for finding the multiplicative inverse in the RSA? So let us understand before that, when we apply a modulus operation, the result of A mod n is always a non-negative integer which is less than n. That particular modulo operation creates a set called set of least residues of modulo n, which is denoted as Zn. So let us take a set called Z11, which contains residues which we obtain by performing modulus operation of that number on various integers. So in this case, the operation is done with the number 11. So when we apply mod 11 on any integer, we get the remainder values from 0 to 10. So this is the set of least residues. So we also understand here the congruent operation, wherein which we show that two integers are congruent when we use the congruent operator. So 2 is congruent to 12 at mod 12. Similarly, 13 is congruent to 23 at mod 10. 8 is congruent to 13 at mod 5. We use congruent operator also in RSA algorithm. Now we look at the inverses. When we are working on modular arithmetic, we look for inverse of a number which is relative to a particular operation. We have two inverses. One is additive inverse. We are also going to have multiplicative inverse, which is relative to multiplication operation. So what is a multiplicative inverse? When we have two numbers A, B, when we multiply them with the result is congruent to 1 mod n, we say A is the multiplicative inverse of B, or B is the multiplicative inverse of A. In a modular arithmetic, an integer may or may not have multiplicative inverse, whereas an additive inverse certainly will have for any integer. So when multiplicative inverse exists, the product of the integer and its multiplicative inverse is congruent to 1 mod n as written here. Now let us see extended Euclid algorithm finding the multiplicative inverse of a particular number in Zn. When n and b are given and the GCD of n comma b is 1, we can find the multiplicative inverse. How do we do that? We use the extended Euclid algorithm to find multiplicative inverse. The process is same as we discussed. We are going to skip the S process, finding that S variable, and the GCD part and the T part remains. So if you see here, the GCD part, we are going to assign the R variable and update the R variable and proceed to find the GCD. Similarly, we assign the T variable and continue to proceed updating the T variable. Finally, once we have the remainder as 0 and when we are able to find the GCD of R1 and the corresponding T1 is the multiplicative inverse of the given number. So let us look at with an example. Imagine we are looking for multiplicative inverse of 11 in Z26. So that means we are having n is equal to 26 and the number for which we are going to find the multiplicative inverse is 11. So take the R1 as 26, the number as 11 which is R2, and we find the quotient and corresponding remainder, and we assign T1 as 0, T2 as 1 as we discussed earlier, and we find the T, and we iterate the process of reassigning or updating the variables. R1 is updated as R2 and R2 is updated as R. Similarly, T1 is updated as T2 and T2 is updated as T. And the process continues. The moment we get the remainder as 0 and the GCD value as 1, we are going to have the multiplicative inverse value of 11 as minus 7. Either we consider as minus 7 or 26 minus 7, 19 is the multiplicative inverse of 26 at multiplicative inverse of 11 at 26. Let us look at one more example. Let us find multiplicative inverse of 23 in Z100. So R1 is 100, number for which we need to find multiplicative inverse is 23 assigned to R2, and the iterative process continues, and we have remainder value as 0, so the GCD value is 1, and hence we are going to have the T variable 13 minus 13 is the multiplicative inverse of 23. Otherwise, we can also consider 100 minus 13, which is 87, as the multiplicative inverse of 23 in Z100. This is how we use extended Euclid algorithm to find the multiplicative inverse. Imagine if suppose we are going to wanted to find multiplicative inverse of 12 in Z26. You notice that we have the remainder value is 0, but the GCD value is not 1, so it is 2. So and hence for 12 we cannot get a multiplicative inverse in Z26 because they are not relatively prime. So this is how extended Euclid algorithm is used to calculate